Investigating Energy Conservation by Michaela Calverley, Emily DeDwyer, and Macy Zach. This semester in LB273, we have discussed momentum and have recently began talking about energy systems. We have learned that an elastic collision is when total kinetic energy is conserved, and that when there is conservation of energy, it means that the amount of energy remains constant and energy is neither created nor destroyed in the system. For our project, we use these ideas and apply them to our findings in order to try and understand the equation for kinetic energy. As I previously stated, our experiment was designed in order to prove the equation for kinetic energy as valid. With the use of one bouncy ball, we were able to keep mass constant throughout all of our trials. In order to prove the kinetic energy equation is true, we dropped this ball from 4 different heights with the goal in mind of discerning why each part of the kinetic energy equation is necessary. After conducting this experiment, we found that the equation for kinetic energy is valid, as the kinetic energy right before the ball hit the ground was equal to the potential energy right before the ball dropped. This showed a transfer of energy from mostly potential to mostly kinetic, which is what we had predicted. Throughout our experiment, we used one bouncy ball with a mass of 90.6 grams, which was provided to us by the physics teaching team. With the use of the tracker software, we dropped this ball from the heights of 0.5 meters, 1 meter, 1.5 meters, and 2 meters in order to collect our data. We also used the equations for kinetic energy and potential energy when doing calculations for our project.
As for the assumptions in our experiment, we assumed mass remained constant by using the same bouncy ball throughout all 4 trials. In addition, acceleration remained constant due to gravity. In our calculations, we assumed gravity was negative 9.81 meters per second squared. At the start of the drop, there's only gravitational energy. However, just before the ball bounces off the floor, the majority of energy is now kinetic. Finally, our data from tracker will give accurate readings in order to make an assumption about the kinetic energy equation. To demonstrate the different types of energy throughout the ball drop, we created 4 different pie charts. The first pie chart presents the ball at rest. Then the ball begins to fall. Then the ball is just above the ground, and finally the ball is coming closer to the ground. In these pie charts, it is shown that at rest, when holding the ball, there is only potential energy. However, as you go down, towards the end, when the ball is about to hit the ground, there is a majority of kinetic energy. Furthermore, we created a schema that depicts the event in which the ball is dropping. There is the ball and the ground, and between the ball and ground, there is contact and gravity.
For our first trial, we dropped the bouncy ball at a height of 0.5 meters. The positions and velocities appeared negative because of the way tracker recorded them. However, they produced the same results as if they were positive. We recorded a video of the ball dropping and then used tracker to measure the velocity of the ball frame by frame. We then made the graphs at the right of this slide with that data. If you focus on the middle graph of velocity, you will see that the velocity decreases and then spikes, only to decrease again. The specific velocity we used in each trial is the lowest velocity before the first spike. This number is in the chart and pointed out by the arrow. The height at this velocity is another value of importance and was also recorded. These same steps were taken in each of the following trials. As was said in the previous slide showing the pie charts and schemas, potential energy right before the ball is dropped should equal the kinetic energy right before the ball hits the ground. So I set the potential energy and kinetic energy equations equal to each other, and then looked to see if they were actually equal, or close to it. Before going through the calculations, I went through and simplified the equations by canceling out mass, and it is constant throughout the whole of the experiment. Then I went and found the total distance the ball fell by subtracting the height where the velocity was recorded from the height dropped. Then I just plugged and chugged until I produced what you see after each arrow. We found that the values produced are equal enough to verify the kinetic energy equation, although our numbers are a bit off due to error. The calculations prove that the kinetic energy equation is valid. However, it doesn't explain why there is 1/2. The answer to that question is that's just how it is. There's really no reason except that it works, and you can see that in the graph above. When you graph height times gravity versus velocity squared, you get the slope of about 1/2.
Like many great experiments, our experiment had errors. These errors included inconsistent heights at which the ball was dropped. Air resistance was not taken into account during our calculations. However, this error was very small. And finally, the tracker calibration was not 100% correct. To conclude our experiment, we did indeed find that the kinetic energy equation is valid. We identified that when comparing the height and velocity squared, the slope was 1/2, and this showed us the 1/2 part of the kinetic equation. In addition, velocity must be squared in order to get a valid kinetic energy value, and this is seen throughout our calculations. Finally, potential energy right before the ball is dropped should equal the kinetic energy right before the ball is about to hit the ground. Thank you for watching our Investigating Energy Conservation video.